So that's how that works. Now, there's an intermediate step that is incorporated in the exercise, which is bagging. And all bagging is, you can bag using iPred. No, let's see. Let's make sure. You can bag with the bagging function. Let's take a look. And what bagging does is it just simply will randomly sample and rearrange the training data set. Think what we did. We randomly selected 70% and said, this is the training data set. We grew one tree, and then we tested it with the remaining 30%. What if we did that over and over again? What if we randomly sampled 70% of the original 150 observations for iris, or the original 71 observations for body fat, and we grew a tree, and then we tested on the remaining test? But we do that over and over again so that each training set is different because it's a random 70%. That's what bagging does. And the default is 25 trees, and it will average the predictions. It will average the errors across the set of trees that it grows. Or you can do it any number of times. You can randomly select 70% 100 times, and each time grow a different tree. Now, that's very similar, and you get an estimate of the out-of-bag error rate. The out-of-bag error rate. What the out-of-bag error rate is, it's the errors that are generated when you do not use the training data. So the out-of-bag error rate is very important, is a critical criterion for assessing accuracy, because it's not the data that you've used to train on. But when you use the out-of-bag estimate with bagging, you're doing it over and over again. So you get less variability. Each tree is going to be variable, but if you average over a number, it's not. Now, random forest is different. With a random forest, you're not resampling training data sets. You are growing a number of trees on the same training data. 50, 100, 500 trees. But random forest adds randomness to the tree growing by using different selection variables. It will consider only a limited subset, and in some cases a random subset of the prediction variables to choose to make the first split. So what you get is you're training on the same training data set, but the trees randomly select which variable to use to split it first among some limitations, some constraints. And so it combines the power of resampling with the randomness or the regression to the mean that is effect that is created when you do it over and over again. So instead of getting widely variable results, they converge. You average it across all the trees, and it's better. It's more consistent, and you get a lower error rate. Random forests are an ensemble approach, very powerful, and they combine the tree with the resampling variable reduction properties of bagging with the variable reduction properties of an ensemble approach where you do it over and over again. So let's take a look at random forest. So here we're going to use iris, and here we do it. Let's do it. So we say split it 70-30. 70% training, 30% test. We call up Random Forest, and I'm running an older version of R, and I do that deliberately. There are those who will go out and install the latest version of R immediately, but I know from experience it's a good idea to lag one or two versions. It can get you in trouble, like it did with my software, where Gaston Sanchez updated PLSPM just in the most recent version, and so I built all these algorithms on the old one. But sometimes you're better off not jumping to the newest technology until it's been out there for just a little bit. Okay, so there are some problems with Random Forest. It does not like missing values, and there are only 32 levels that it can use for any one categorical variable, which is really a lot. So, but basically the approach is very similar. There's our formula, tilde as a function of everything, dot means everything. And we'll use the training. We're going to grow 100 trees. And I always forget what proximity does. It's a good idea to look at the function. Here's the function. And we find proximity, should the proximity measure among the rows be calculated? No wonder I can't remember that. I'm still not sure what that does for us. Basically, we're just going to grow trees using, in many cases, a different selected variable for the first split, but we're going to do it 100 times. Okay, so we do that. We're going to put the output in RF. So we run that, and then we're going to predict using the training. This is the original data. We're going to do tabulation, confusion matrix. So on the original data, it did really well. This is, again, Iris, but this is 100 trees. And in fact, the predictions are, the rates are lower. But if we look at the results, there's our class error is very low. And attributes, notice with the tree, you have all of these in the fitted object, in the random forest, not the tree, the random forest. You have a wider variety of fitted properties, like importance. This tells you which variables are the most important in determining this first split. And I don't know what a lot of these other ones do, but you have more reporting ability. You can glean more insights about your tree because all of these fitted criterion are available to you to look at. Okay, so random forests really are at the top of the heap as far as powerful prediction data mining techniques. Okay, so here's another thing you can do with a random forest. We can plot. When you draw a plot, note this is Iris. It's showing us along the horizontal, this is the relative error rate, which when the forest is a very small number of trees is very high. Each colored line is a different variable. And each one is a different variable. We had the four variables, and it's showing us as the number of trees go up, you can see that the error rate goes down to a point when there are approximately 40 plus trees, or maybe right here, the error rate is at the lowest. So what that tells you is, for this data set, it doesn't make sense to use 100 trees. There's no additional power for a larger forest. In fact, once you get beyond about 44, you pretty much have bottomed out. Okay, but also it shows the relative importance of the variables through the mean decrease in Gini, and this is the one that I'm still trying to run down the precise definition of. Gini is a diversity index, shows the purity of the splits on each side, but it's not just the classification ability per se. There's a twist to it. But what you want to look for is the variable with the biggest mean decrease in Gini. That's where you're getting all of your power, and it's petal length. And you can plot these. So that gives you the importance with the Gini criterion, and you can plot them, which more visually we can see that there's a big gap here between these two and these two. In fact, these two really are way out in front, and so what we can imply or infer from this is that sepal length and sepal width really don't contribute much at all. That it's these two variables that are the most important in terms of classification error. Actually, this is mean decrease in Gini, but it's very close. It's very akin to classification error, but it's not quite exactly the same. Okay, and then we can predict. But what we really want to do is see how the random forest does with predicting with the new one. So with the test data, so we do that. And actually, it's not quite as good. Sometimes when the numbers are small, it depends on the numbers that you have in the training and test set, and it depends on the diversity. If you got a lot of variability in the data, you're going to get more variability in the predictive outcomes and so forth. But generally speaking, random forests are better than trees and better than bagging. Bagging is usually better than a single tree. Okay, so it also gives you this plot against the margin, which is simply, it shows you the reduction in error based on the number of trees, but tied to each variable. We have 4 predictive variables, and we have 4 colors here. 3, okay, 3 predictive variables, 3 that ended up. We have green, we have blue, we have red. And we note each one relates to a different variable. And we note that the error rate is getting better. The accuracy is getting better as the number of trees in the forest increases. But you can see that marginal improvement for each variable up to here, and then it pretty much flattens out. Okay, so much for that. Now, let me show you 46. We don't have a lot of time. So I searched for exercises, and I found one that was close, and so I modified it. This is really a good one, I think. It's appropriate, where you build a tree, you bag, and you build a random forest, and then you compare them. So we extend, if you go through this, the parts that we've covered in class, I ask you to put your code in. Okay, so you ought to be able to do that. The parts we did not cover in class, and most of it we did cover, like bagging. Actually, I ask you to look up the bagging function, so you should be able to figure out how to do it. And then random forest. So you build a tree, you bag with resampling, and you build a random forest, and you look at the results for each one. And this is a new data set. And throw a couple of extra plots at you here about importance. 2 measures of accuracy. There's decision accuracy per se, and there's the Gini index. And they're related, but they're not quite the same. Okay, and then we use functions in the IPRED packages that the function specifically is error est in IPRED, from which you can compare the results of the predictions for any technique you use, tree, bagging, random forest. And that's what we do down here, and you can see the out-of-bag error rate. So you can compare and see which one is best.